The sun's changes from August to December are primarily related to Earth's axial tilt and orbit. During this period, the northern hemisphere experiences autumn, characterized by shorter days and cooler temperatures. As Earth's axial tilt causes the sun's angle to decrease, the southern hemisphere experiences spring, with longer days and warmer temperatures, as the tilt allows the sun's rays to hit more directly. These changes are due to Earth's motion and tilt, not the sun's movement in the universe.
Subscribe and like our channel and click the bell icon. Thanks.
Around September 22nd, the northern and southern hemispheres experience an equinox, where day and night are approximately equal in duration. This marks the beginning of autumn in the northern hemisphere and spring in the southern hemisphere. Solar declination refers to the angle of the sun above the Earth's equator. As the months progress from August to December, the solar declination decreases in the northern hemisphere, leading to low sun angles and shorter days. Conversely, the southern hemisphere experiences an increase in solar declination, resulting in higher sun angles and longer days. As the sun's angle changes in the sky, the quality and color of light during sunrise and sunset can also vary. The lower angle of the sun during these months often leads to more colorful and dramatic sunrise and sunsets, with hues of red, orange, and pink illuminating the sky. The position of the sun in the sky affects which constellations are visible during the night. As the months progress, different constellations become prominent. For example, during August, the constellation Leo might be visible in the early evening, while by December, the constellation Orion might take its place. The sun's path across the sky changes as the Earth orbits the sun in the northern hemisphere. During this period, the sun appears to move lower in the sky each day, resulting in the sun's position being more to the south. In the southern hemisphere, the sun's path moves higher in the sky, toward the north. While not solely tied to the months of August to December, variations in solar activity can influence the occurrence of auroras, also known as the northern and southern lights. These stunning natural displays of light are more likely to be observed in regions closer to the poles during periods of increased solar activity. During this period, the time of sunrise and sunset gradually shifts. In the northern hemisphere, sunrise occurs later and sunset occurs earlier as the days become shorter. In the southern hemisphere, sunrise occurs earlier and sunset occurs later as the days become longer. The sun continually emits a stream of charged particles known as the solar wind. Variations in the solar wind's speed and density can influence space weather conditions around Earth, affecting satellite operations, communication systems, and even power grids. The sun goes through an approximately 11-year solar cycle. Although not strictly tied to the months of August to December, solar activity, including sunspots and solar flares, can vary during this time frame. Sunspots are areas of magnetic activity on the sun's surface that can impact space weather and Earth's geomagnetic conditions. While not solely tied to the months of August to December, variations in solar activity can influence the occurrence of auroras, also known as the northern and southern lights. These stunning natural displays of light are more likely to be observed in regions closer to the poles during periods of increased solar activity. The sun's surface can exhibit dynamic features like solar prominences, huge loops of gas, and solar flares, sudden bursts of energy and radiation. These phenomena can occur at any time of the year and are influenced by the sun's complex magnetic field. Solar panels generate electricity from sunlight. As the angle of the sun changes and daylight hours shift, photovoltaic energy production can vary. In some regions, photovoltaic systems may experience slightly reduced efficiency during the late fall and winter months due to the lower sun angle and fewer daylight hours. Such as from August to December, The Sun is a stable star that follows its own relatively predictable life cycle, and its position within our Milky Way galaxy remains relatively constant over short time periods. The Milky Way galaxy itself rotates, and the Sun moves along with it. This rotation is also on a timescale of hundreds of millions of years. The Sun oscillates slightly above and below the plane of the Milky Way galaxy over very long timescales. This motion, known as vertical oscillation, occurs over tens of millions of years. The Milky Way is part of a larger cosmic structure, and its position within the universe changes as galaxies interact and move over billions of years. However, these changes are not noticeable on human timescales. The Sun, along with the entire solar system, is moving through space at an average speed of about 230 kilometers per second, 143 miles per second. This motion is a result of the gravitational interactions between the Milky Way's various components, including its spiral arms and central bulge. Over extremely long timescales, the Milky Way interacts with other galaxies. Collisions and mergers with other galaxies can influence the distribution of stars, gas, and dust within the Milky Way, and may alter the Sun's position within the galaxy. The solar apex is the direction in which the Sun is currently moving relative to the local stars in its vicinity. The Sun's motion is influenced by the combined gravitational effects of nearby stars and the overall structure of the Milky Way. The Sun's motion and position are influenced by the gravitational pull of the Milky Way's dark matter halo, which extends beyond the visible boundaries of the galaxy. The dynamics of dark matter and its interaction with visible matter play a role in shaping the Sun's journey through the universe. While the Sun is relatively stable over human timescales, it does undergo long-term variations in its behavior, including changes in solar activity, sunspot cycles, and overall energy output. These variations occur over periods of decades to centuries and can have subtle effects on Earth's climate and space environment. The Sun is currently located in a region of space known as the local interstellar cloud, LIC. This is a relatively tenuous and cold cloud of gas and dust that surrounds our solar system. The Sun's interaction with the LIC can influence the properties of the solar wind and the heliosphere, the protective bubble created by the solar wind. While the Sun's changes over the course of a few months are minimal, on much longer timescales, billions of years, the Sun will eventually exhaust its nuclear fuel and undergo significant changes. It will expand into a red giant phase and then shed its outer layers, forming a planetary nebula. The remaining core will become a white dwarf. The Sun is part of a larger group of stars known as the local bubble. This is a cavity in the interstellar medium that was created by multiple supernova explosions. The Sun's position within the local bubble has implications for the environment of our solar system, including the density of interstellar gas and cosmic rays. As the Earth orbits the Sun, we observe different parts of the night sky at different times of the year. This leads to the phenomenon of stellar parallax, which allows astronomers to measure the distances to nearby stars by observing their apparent shifts in position. The Sun is estimated to be about 4.6 billion years old and is roughly middle-aged in terms of its stellar evolution. It has been shining steadily for most of its existence, and its energy output has gradually increased over time. The solar wind produced by the Sun creates a bubble in space called the heliosphere. As the Sun moves through the galaxy, it encounters the interstellar medium, The point where the solar wind slows down and transitions into the interstellar medium is known as the solar wind termination shock. While the sun's position in the universe doesn't directly cause short-term climate changes, variations in solar activity, such as changes in sunspot cycles and energy output, can influence Earth's climate on longer timescales through mechanisms like the Maunder minimum, a period of low solar activity associated with cooler temperatures on Earth. The sun's magnetic field undergoes a complete reversal approximately every 11 years, coinciding with the peak of the solar activity cycle. This phenomenon is known as a solar magnetic field reversal or solar magnetic flip. Occasionally, comets from the outer solar system pass very close to the sun. These sun-grazing comets can reveal information about the sun's atmosphere and magnetic fields as they interact with the intense solar environment. Solar eclipses occur when the moon passes between the Earth and the sun, temporarily blocking out the sun's light. These events provide valuable opportunities for scientists to study the sun's outer atmosphere, or corona, and gather insights into its composition and behavior. Scientists study the sun's interior by observing its surface oscillations, similar to seismic waves on Earth. This field of study, known as helioseismology, helps us understand the sun's internal structure, rotation, and magnetic activity. The sun is classified as a G-type main sequence star, G-dwarf star. It is currently in the middle of its life cycle, during which it fuses hydrogen into helium in its core. This phase, known as the main sequence, lasts for billions of years. The solar wind, a stream of charged particles emitted by the sun, has a profound impact on the shapes and structures of celestial bodies in our solar system, including the tails of comets and the shapes of planets' magnetospheres. Sunspots are temporary dark spots on the sun's surface caused by intense magnetic activity. Solar flares are sudden releases of energy that can cause bursts of radiation and disrupt radio signals and communication systems on Earth. The sun has held immense cultural and religious significance throughout human history. Many ancient civilizations worshipped the sun as a deity and built monuments aligned with its movements. The sun's motion through the universe causes a slight Doppler shift in the cosmic microwave background radiation, a faint glow left over from the early universe. This effect provides insights into the universe expansion and the sun's trajectory. Telescopes and spacecraft dedicated to observing the sun, such as the Solar Dynamics Observatory (SDO) and the Parker Solar Probe, provide valuable data about the sun's dynamic behavior, magnetic fields, and solar phenomena. The sun's light is composed of a continuous spectrum of colors, but it also contains absorption lines caused by the elements present in its outer layers. By analyzing these absorption lines, scientists can determine the sun's composition.